session of the VLab Forum. This is Steve Smith, Director of the VLab, and I'm joined here in Silver Spring, Maryland, along with John Chattel, who is our Technical Production Manager of the VLab. He will be manning the GoToMeeting during this session. The format of these sessions are we have 30 minutes of presentation followed by about 30 minutes approximately of question and answer. We request that you hold off your questions until the Q&A session unless it's an urgent or important point of clarification. To ask a question, you can use the, we encourage you to use the raise your hand feature in the GoToMeeting and select that on, and John Chattel will be monitoring that during the Q&A session. He will unmute you to allow you to ask your question directly to the speaker. Alternatively, you can ask a question through the chat feature in the GoToMeeting webinar. Those in the room, of course, can ask the question directly to our speaker. And with that, today's topic is evaluation of NCAR's AutoNowCaster for operational application with the National Weather Service. The speaker for today's talk is John Crockett of the Meteorological Development Lab and the Cooperative Institute for Research in the Atmosphere in Fort Collins, Colorado. As usual, I like to point out the purpose, or one of the purposes of the VLab Forum is to provide exposure and situational awareness of new guidance products, forecast products, tools, observing systems, observations, whatever that may at some point in the future make their way into Weather Service operations or NOAA operations. In this case, the AutoNowCaster is been, as you'll hear more about this in a moment, is part of now the version 11 of the MRMS system, which is currently in transition to NCEP operations. So this one is coming in the near future, and the purpose is to provide some background information on that and allow folks to ask questions. And a further point of disclosure, the AutoNowCaster project is one under my purview as a branch chief in the Meteorological Development Lab, so I'm very familiar with the project from that point. So without further ado, I'm going to hand over the mic to our speaker, John Crockett.
Good afternoon, everybody. Welcome again to the June VLab Forum. This is John Crockett, and I will be presenting an evaluation of NCAR's AutoNowCaster for operational application within the National Weather Service. Next slide. First, let me begin by introducing the AutoNowCaster, or ANC, team, both here at the MDL and at NCAR. Federal members of the team are Steve Smith, the Decision Support Branch Chief, Ama Ba, who is the Project Manager, and Lingyan Xin, who is our Verification Analyst. Ken Sparrow, my predecessor, and I are technical leads as cooperative researchers from CIRA. And at NCAR's Research Applications Laboratory, Rita Roberts was Principal Investigator, and Daniel Megenhardt was my and Ken Sparrow's technical counterpart. Next slide. Here's a brief overview of the history of ANC here at the MDL. Top portion of the timeline is meant to show that from its beginnings here at the MDL until the current time, the domain over which we have run ANC has slowly but steadily increased, beginning with an WFO level domain at Dallas-Fort Worth up to the present day where we run ANC over the entire CONUS. The bottom portion of the timeline is meant to show periods and points in ANC's history here at the MDL. I wish to call specific attention to the verification data collection period of time in 2012, from which the data for our current evaluation. Also would like to point out that currently the Aviation Weather Center is already using ANC in an experimental capacity to help it issue 2-hour convective SIGMETs. And as Steve mentioned in the introduction, fingers crossed, ANC will become operational at NCEP in September of this year as a subsystem within MRMS version 11. Next slide. So what is ANC and how does it do what it is supposed to do? From its early days in NCAR, ANC has been designed to nowcast areas where storms are considered likely to form and or be sustained and vice versa. How does it do this? It ingests a variety of data in order to analyze characteristic features of the atmosphere. The results of these analyses are 60-minute predictors. These predictors are converted into dimensionless likelihood fields. Those likelihood fields range in value from -1 to 1, where increasingly positive values correspond to an increasing likelihood of storm initiation and or sustainment, and vice versa. Those dimensionless likelihood fields are weighted and summed to give ANC's predicand a 60-minute nowcast of convective likelihood. So in essence, ANC attempts to analyze, weight, and sum various data in a manner analogous to that of a forecaster. Next slide. So what are these predictors which are used by ANC? 3 of the predictors used by ANC are meant to assess the dynamics of the environment. One of these is the likelihood of a frontal zone occurring in 1 hour. The second is the surface convergence in 1 hour. And the third is the vertical velocity at the 700 millibar pressure level in 1 hour. Next slide. 5 of ANC's predictors are meant to assess the thermodynamics of the environment. First of these is the average relative humidity in 1 hour between the indicated pressure levels. Also included is the lifted index in 1 hour, the maximum cape in 1 hour between the indicated pressure levels, the mean sin in 1 hour between the shown pressure levels, and an index of vertical instability between 1,700 millibars 1 hour hence. Next slide. The last 2 of ANC's predictors deal with clouds. The first of these is the likelihood of convective clouds being present or absent in 1 hour. The second is the infrared rate of change at the tops of those clouds which are considered to be convective 1 hour in the future. Next slide. So using these predictors and predictor-specific fuzzy functions, which were developed by the relevant experts at NCAR who have dealt with this over a number of years, those predictors are converted into dimensional likelihood fields, weighted as shown, summed in order to give what you see in front of you, a 60-minute nowcast of convective likelihood. Next slide. So how does this look in real time? Here you have an example time series of 60-minute nowcasts of convective likelihood on July the 1st in 2012. Overlaying these nowcasts are the contours of 35 dBz at the valid time. Reading from left to right and top to bottom, one sees that initially in this particular time series that ANC assesses the environment to be quite stable. But as time progresses, ANC begins to assess and continues to assess the environment as becoming increasingly unstable. And at the valid time shown, one sees that in fact, a number of storms have developed in areas in which ANC has assessed the environment to be appropriate. However, one sees in the top 2 rightmost diagrams that in fact storms have developed in areas where ANC assessed the environment to be quite stable. This leads to the question as to exactly how one is to assess the accuracy of ANC in this case. How do we measure the performance of these nowcasts of convective likelihood? Next slide. Over the course of our evaluation period, we went down a number of paths in order to answer the basic question of how one can assess these nowcasts. I present these 3 questions in summary of where our investigation led us and which I will address as part of this presentation. The first question is, what is the smallest spatial scale at which ANC's 60-minute nowcasts of convective likelihood can skillfully nowcast the general areas where both new storms may initiate and existing storms should be sustained, and to what values of convective likelihood does this apply? The second question is a modification of that. What is the smallest spatial scale at which ANC's 60-minute nowcast of convective likelihood can skillfully nowcast the general areas solely where new storms may initiate? And to what values of convective likelihood does this apply? Now, the difference between these two questions stems from the initial thrust of ANC's research and development at NCAR. NCAR has maintained and has done much research and development into the nowcasting solely of convective initiation. That was the initial thrust at NCAR. However, in our experience here at the MDL over a number of years, and specifically through the direct and constant observation of ANC by Amma, the project manager, it has been seen that ANC has the potential and could be used not only to nowcast convective initiation, but also to nowcast the general instability where storms, existing storms, might be sustained or could be sustained, or into which, if storms move into that environment, would continue to be sustained. So that is why we have these two questions, similar but not the same. The last question, which we also found ourselves needing to address as part of this evaluation, is to what degree, if any, are ANC's 60-minute nowcasts of convective likelihood subject to temporal ambiguity? Next slide. So the domain for the study is shown here. We have dubbed this the Golden Triangle domain, the reason being that this particular area contains within it the triangular area between the Chicago, New York, and Atlanta airports, an area of particular concern to the FAA and also to the Aviation Weather Center as it uses ANC to issue its 2-hour convective SIGMETs. Next slide. What were the data we used for this evaluation? Well, of course, we needed to use ANC's nowcast grids for this. For those nowcasts, we used 55 days worth of data from mid-June through late September of 2012, the convective season, or a large portion of the convective season here in the United States. And generally the data come from what is 10 a.m. to 8 p.m. Eastern time in the United States, given the area which we were evaluating. The truth grids which are used, or the observations, are not as direct as might normally be the case. Radar data do not in and of themselves distinguish between initiation and ongoing storms. So in order to assess ANC's ability to nowcast skillfully solely convective initiation, we were confronted with the problem of how we determine what in radar data is new initiation, what is ongoing, etc. To do that, we made use of our WSR88D reflectivity volumes, first filtered for brightband, then filtered for stratiform data, and composited between 2.5 and 4.5 kilometers inclusive. Those particular filtered composites were then fed into a slightly modified version of an application which is part of the Warning Decision Support System Integrated Information Suite. That application's output is a grid in which each grid point is assigned a value which identifies the corresponding grid point in the second composite of each pair of composites as either a newly initiated storm element, an ongoing storm element, a decaying storm element, or none of the above, where a storm was defined by us to be any radar echo greater than or equal to 35 dBz. It is those observation grids output from that classifier which we used as the truth grids against which to compare ANC's nowcasts. Next slide. So how did we calculate the statistics for this verification? Within any given hour of data, ANC normally output approximately 10 nowcasts. The number could be smaller depending on data ingest problems, glitches, etc. So generally 10 nowcasts per hour, sometimes fewer, in general than 1 to m nowcasts in any given hour of time. So with those 1 to m, we have the n nowcasts, our constructed observation grids, and from each pair, we're able to construct a verification grid in which the number of hits, misses, false alarms, and non-events could be calculated. We summed those verification statistics for the verification grids for an hour to have a total number of hits, misses, false alarms, and non-events in an hour. And from those totals, calculated the standard statistics of the probability of detection, false alarm rate, bias, critical success index, and we also calculated the Heidke skills score in order to accommodate the fact that non-events dominate when nowcasting convective initiation. Next slide. When doing our verification, we did not attempt to match exactly the forecast value at a grid point with the observed value at the same grid point. Rather, we implemented the well-known neighborhood verification scheme whereby forecasts and observations were compared using spatial neighborhoods around grid points. The neighborhood size parameter m for that particular scheme yields a 2n plus 1 by 2n plus 1 neighborhood around any grid point. Varying the neighborhood size parameter helps determine the scale at which a desired level of skill is attained by the nowcast of convective likelihood. Such verification rewards closeness by not requiring exact matches spatially between the nowcasts and what was observed. Next slide. So here we have the first set of results. Harkening back to the first question we asked, or found ourselves asking, how skillfully can ANC nowcast the not only convective initiation but also ongoing storms together? For our verification, we used 4 different neighborhood size parameters, which result in 4 different linear scales. From left to right, you see a verification here at the 10-kilometer scale level, then the 25-kilometer scale, 50-kilometer scale, and 100-kilometer scale. For this particular verification, we said that a forecasted event consists of a now grid point whose convective likelihood value was greater than or equal to 0.6. Question arises, why 0.6? In NCAR's research, NCAR determined that a convective likelihood value greater than or equal to 0.7 most often, or what could be considered to correspond to nowcasting convective initiation solely. So in our thinking, in order to capture not only convective initiation, but the instability where storms can continue and be sustained, we lowered the value of the convective likelihood down by 1/10 to see what the skill level could be. This shows our results in this regard. So at the 10-kilometer scale, it's quite clear to us that ANC does not possess skill when nowcasting both convective initiation and the areas where storms can be sustained. At the 25-kilometer scale here, the skill increases, and some might argue that with a median CSI of 0.3, that is quite good. However, we do not consider that to be good enough in this regard, and we take the next one, 50-kilometer scale level, with a median CSI of 0.5 to be a more appropriate scale at which ANC skillfully nowcasts both convective initiation and the areas where storms may be sustained. Of course, at the 100-kilometer scale, life is great, and those are great scores. But getting back again to our question, we are looking for the smallest scale possible at which we consider ANC to nowcast such events skillfully. So for this particular verification, we would say that is the 50-kilometer scale. Next slide. Of course, the definition of a forecast event itself can change the output of your statistical analysis. Having started at 0.6, we chose to lower the threshold of convective likelihood and to forecast or begin to evaluate how ANC nowcasts both new initiation or ongoing storm environments. Getting back to the original idea that the likelihood fields created by ANC have a dynamic range from -1 to 1, where increasing values are considered to be more indicative of instability. We see here basically a confirmation of that idea in the sense that as one lowers the convective likelihood, the actual skill of the nowcast decreases. We are increasing the false alarm rate by lowering the threshold. So we accept at this time that a convective likelihood value greater than or equal to 0.6 at a 50-kilometer scale is represents a good combination to consider when evaluating these nowcasts. Next slide. Having looked into question number 1, we then looked into question number 2. How skillfully can ANC nowcast solely convective initiation? So we began at the same starting point as the first question with the 4 different scales in front of you and with a forecast event being defined as convective likelihood values greater than and or equal to 0.7. We see here once again that at the 10-kilometer scale, there is no skill whatsoever in nowcasting solely convective initiation. At the 25-kilometer scale, things have gotten better, but that is still not nearly good enough to do what we want ANC to be able to do. At the 50-kilometer scale, the scores have increased, the probability of detection is higher, but the median CSI is still hovering in the 0.3 range there. At the 100-kilometer scale, to be expected, things are a lot better, but that is one scale level above what we have determined ANC's ability to nowcast both initiation and general instability as. So thinking about this, it was Amma's observation over the period of this study, and he looked at it every day. So a wide spectrum in terms of number of days, times of day, different environments over the study area. And it was his observation that when ANC showed areas where the convective likelihood values were 0.7 or above, if it maintained that level of instability for a certain period of time, 1, 2, or 3 hours, something almost always happened within the areas where those, or within or around the areas where those values were seen. But what he noticed is that they were not always at the time of the expected valid time. They would rather be spread out a little bit around that valid time. So it occurred to us that we may or should need to incorporate temporal ambiguity into this study to see how much time, what is the window of time around a valid time where what we're seeing could be considered as such that ANC's nowcasts are skillful both in space and in time. So, next slide. So what we did is we incorporated temporal relaxation into the evaluation. So as time is represented on the left with increasing time going downward, at the valid time we had our the observation grid, which we had already calculated and against which we had calculated our statistics. But about that time, some window, valid time minus some period of time, t minus, and or plus some period of time, t plus, there would be a range of these observation grids which we had created. If there were, at any point within this window of time, the classifier had classified something as being new initiation, then in the composite through time of these grids, that same grid point in the composite would be flagged as having new initiation. It was these composite observation grids that we then used to rerun our statistics against the corresponding nowcast to see what windows of time might correspond or need to be considered when assessing ANC's nowcast. Next slide. So here we have the results for the two smallest of the scales which we considered. The two diagrams on the left show the 10-kilometer scale using two different windows of time, 15 minutes on either side of the valid time, the second being 30 minutes on either side of the valid time. The rightmost two show the 25-kilometer scale, again, 15 minutes on either side of the valid time, and the rightmost being 30 minutes on either side of the valid time. This is attempting to nowcast solely new initiation. Again, looking at the 10-kilometer scale, we take this to mean that there's no skill in trying to nowcast solely convective initiation at the 10-kilometer scale, no matter the window of time you use. At the 25-kilometer scale, the windows of time provide a much higher degree of skill than they had possessed without the windows of time being used. But still, we wanted to see how that would correspond to when we go up to the next skill level, also using these windows. The next slide. So, excuse me. So the leftmost column is our 10-kilometer scale. The middle column is our 25-kilometer scale. The rightmost column is our 50-kilometer scale. The topmost row is that window of time, 15 minutes on either side of the valid time. And the bottom row is the 30 minutes of time on either side of the valid time. Looking at this, we assess this to mean and conclude that it's again at the 50-kilometer scale with a median CSI of around 0.5 or so, all the way up to 0.6, that ANC can skillfully nowcast solely new initiation. The windows you see here are not the only windows of time we used. We did consider two other windows of time, the first being 30 minutes beginning at the valid time and going forward with no time before the valid time being considered. Also, we considered the from the valid time onward 60 minutes. In the combination, looking at the different measures of statistical measures from all of those results, which are not all shown here, it was observed and became apparent that the window of time which seems to maximize the skill of ANC's nowcast solely of new initiation is 15 minutes before the valid time through 30 minutes after the valid time. So a 45-minute window seems to be the sweet spot when interpreting ANC's nowcast of convective initiation solely. The next slide, please. So in conclusion, just to again reiterate, it's at a spatial scale of approximately 50 kilometers and with no temporal relaxation. We assess ANC to be able to nowcast skillfully the general areas where both new storms may initiate and existing storms should be sustained. When nowcasting solely convective initiation, it's at a spatial scale of approximately 50 kilometers and within 45 to 90 minutes from the issuance time, grid points with values greater than or equal to 0.7 are needed or what are used as the forecast values. So, and looking back on what the AWC is currently doing with ANC, we consider ANC's 60-minute nowcast of convective likelihood that they can best improve situational awareness when interpreted as guidance at the appropriate spatial scale and within a time frame relevant to what is being nowcasted. Next slide. So, and just in here at the end, for those of you who have downloaded this slide, or I'm sorry, this presentation, the points of contact for this project, for any specific questions which you may have after this forum, can be found here, and a select bibliography for the project is on the final slide. That ends my presentation.
Thank you, John. Excellent overview. Before we turn to questions, I just want to add a comment that to re-emphasize, I guess, one of the distinguishing features of the AutoNowCaster system is this focus and ability to predict new convection. There are literally dozens of nowcasting systems which are based on extrapolation, which take existing radar echoes or satellite-defined storms and use some sort of methodology to advect them into the future based on their current motion. The AutoNowCaster is one of the few, if not the only one, that attempts to capture this new storms and attempt to focus on that initiation piece. So John Chattel, let's turn to the questions. Do we have any on GoTo?
Yes. The folks at Eastern Region, perhaps Ken Johnson, would like to ask a question.
Eastern Region, go ahead.
Yeah, this is Ken Johnson. Thanks for the presentation. I got two questions. The first is, you seem to explicitly talk about likelihoods as opposed to probabilities. Is that because you're talking about likelihoods in a true statistical sense as opposed to probabilities, or what you know, could you clarify that?
The likelihood fields created by ANC are, in fact, they are not statistical probabilities. It is a deterministic system in this regard, and it is not meant to be interpreted. These values of -1 to 1 are not to be interpreted in a statistical fashion at all. They arise from the research at NCAR by people who've invested a great deal of time in understanding the underlying process involved here to make it possible to combine a good number of different fields which could not be combined in any other way in order to assess the instability of the environment in general. So it is not a statistical or probabilistic nowcast at all.
Okay, thanks. That helps clear that up then. So I guess probably my second question isn't maybe so relevant then, but what I was going to ask is there's some convective initiation schemes or approaches, methodologies out there, particularly related to satellite data. There's the Prob Severe, which I think comes out of NESDIS, and the Sport Group down in Huntsville, Alabama, has some convective initiation schemes. I was wondering if there's been any comparison or linkage between those approaches and modes versus the AutoNowCaster.
When you say have there been any comparisons, you mean have we attempted any study to compare which systems may be better, or are you wanting to know whether or not we have, what level of comparison are you talking about?
Well, I was wondering first off if you're aware of them and how those systems might be different from what your approach is, but your approach is more, it sounds like more deterministic. So they may be more apples and oranges in this case.
Yeah, Ken, let me jump in here. So we're aware of these other systems, and at some point in the trajectory timeline that John showed, there was a formal evaluation of AutoNowCaster vis-a-vis other guidance products, but it's safe to say it was limited and not comprehensive. The one thing that the AutoNowCaster system is good for is introducing new predictors into the scheme in order to try them out. So it's conceivable that one could use output from those other systems as predictors in this one if that was suitable. So it's kind of an aggregator of different data, predictive data that could benefit, which makes it flexible in that regard.
Mm-hmm. Ken, what I would also like to point out is looking at this slide, it was at the Aviation Weather Testbed Summer Experiment of 2013, where ANC received its debut, and the Aviation Weather Center actually ranked it in the top 3 of the new products for that year, which it found useful, and sought to move it into its operational setting as quickly as possible. So as Steve mentioned, we ourselves here at the MDL have not done an assessment, which you suggest, but clearly what we've done here has had sufficient value to be used by the Aviation Weather Center itself, and we take that as quite high praise.
Okay, yeah, for example, the Prob Severe methodology that I was talking about has been used in the hazardous weather test bed the past couple of years and has had forecasters really finding that very favorable, and I was just curious if there was any comparison between the two. But okay, thank you.
Sure, but feel free to send us any information to the points of contact at the end of the presentation if you feel that it would be beneficial.
Another important point to bring out that I don't think we brought out was that the verification that analysis has been shown here is on this convective likelihood, which actually is not that's not the actual forecast that the AutoNowCaster produces. And you might say, well, why is that? And the reason is that, first of all, Rita Roberts and company, they did a verification of that and published it in Monthly Weather Review, so that's one thing. But the main thing is that, and when exposing this guidance to forecasters, both in the Dallas-Fort Worth office and in Florida, and certainly in the Aviation Weather Center, consistently the most popular field for them was this convective likelihood. So this was what drove us initially to say, why is that the most popular field? In some sense, it's a question of expectation. So what we found is in Weather Service operations, when you show the actual explicit grid-based forecast, it doesn't always, the storms don't fall where in the grid boxes where the AutoNowCaster predicts. So there was an expectation problem. Then the forecaster saw this and said, well, this is crappy. It's not actually, I'm expecting it to occur right at that grid box. But the sort of broader-based swath that you see in this convective likelihood did act as almost like a convective mask, and it was more coherent in time and space, and therefore the forecasters saw that as something they could rely on. So then we turned, that was Amma's observation, and so we turned to say, well, we need to change the predictan to that, and let's look at that rather than the actual gridded forecast to evaluate. And that's what's been done. John, do we have other questions from the virtual audience?
Online.
In the room. Yes.
That convective likelihood is something that's difficult for me to get my hands around. How is it formulated? Based on this set of predictors that he showed. And including that set of predictors, it was not clear to me where those predictors come from. For instance, you said numerical model output. That can mean a lot of things. I would like to know specifically which numerical models are involved in that, how those different predictors are weighted to come up with this? I call it an index. You call it a likelihood. It seems like it's some sort of an index that has a arbitrary range, as far as I can tell, or somehow defined between -1 and 1. If you can elaborate on that a little bit, it would help me understand what that likelihood index or value really means.
Okay. So let's look at let's go backwards, John. Can you go back 1, 2, 3 slides? Okay. So let's take the rightmost one. Okay, so 700 millibars in 1 hour. So this is actually, so the numerical weather prediction model, which is used by ANC, is RAP. We experimented actually with moving up to the HER, but the delays in time in terms of getting the data are too great at the moment to use them in a rapidly updating situation. So RAP provides our numerical weather prediction model data. So from RAP, so let's just take this field in particular. So why was this field chosen? Okay, so to be clear, the fields which you see here are not chosen, or were not chosen here at the MDL. They represent the culmination of years of NCAR's research into trying to pick those elements of the environment which their experience in research and development made them consider or understand as being an essential element of the mix in assessing the instability of the atmosphere. So, of course, W is not, it has a particular scale to it. In this case, I think the scale there is meters per second, but whatever, it's not combinable directly with any of the other fields. Although those other fields and all the ones you saw during the presentation were considered, as studied by NCAR, to be an element of the mix. So in trying to create a system which could assess the general instability using all of these predictors, they were left with the impossibility of directly combining them. So using, years of research and development. So John, if you can move forward 3 more. So all of those are done that way. So here you see, okay, so look at the second one from the top in terms of the way this gets mixed. So there's that vertical velocity, 700 millibars 1 hour from now. So F sub 2 there is a predictor-specific fuzzy function. So what is this fuzzy function? This is a function created by NCAR in order to translate the values of vertical velocity of 700 millibars into a dimensionless, something dimensionless, which could be combined with the other predictors. Now that, I don't show that fuzzy function here, but the fuzzy function for each of those predictors is different, and they are created by NCAR based on their experience and their analysis and their verification to see, when I combine all of these fields together, am I arriving at something which actually designates or shows where the greatest instabilities are. So yes, it is the final output of that, F sub 2 on that particular predictor. It's not arbitrary in the sense that for each predictor, when it goes through the fuzzy logic, you end up with a value between -1 and 1. So why was that? Well, some of these predictors, for example, second from the bottom, this is derived from the third from the bottom, but the likelihood of clear sky in 1 hour, that, from NCAR's perspective, and true, cannot weight positively or cannot end up with a positive value when nowcasting or trying to assess instability, because clear sky is not, if it's free of convective clouds, you would not say this is adding to instability or is an indicator of instability. You would want that particular element, assessment of the environment, to dampen the possibility that you're going to end up with a value of convective likelihood, which is high. So that is why the fuzzy logic assesses, or for every predictor, is rating it, a sense, changing the scale to something which can be combined for all the predictors. So if you had a cape, for example, the maximum cape, well, if the maximum cape between those two pressure levels is negligible, I mean, it would not be considered by a forecaster or, through their understanding to contribute positively to instability, it will, again, the fuzzy logic function will translate that value into something negative. So in the sum of those, you will end up with some number, okay, which lies between -1 and 1. The weights that you see here, and these are the weights which are currently running, those two are from NCAR, and that was something that they did years of research on to find out what is if which predictor, when translated into a value between -1 and 1, is strongest or contributes either most positively or most negatively. What we've always found interesting, second from the bottom, is the likelihood of clear sky, which has the greatest weight, but it's weighting it the most negatively. Because with clear sky, it's considered such a suppressant. They weight that quite highly in terms of this is most likely not a sufficiently unstable environment to where we would now cast high instability. And likewise with the other weights. So at the end of all this, you've taken a number of different predictors with a number of different units, transform them into a dimensionless field, which can then be combined with the other predictors and weighted accordingly. And this all derives from NCAR's research and development and understanding of what constitutes a sufficiently unstable environment, and how do you assign values to that, and to understand how unstable or how stable the environment is. So that is the genesis of that field, and using those predictors to come up with that single likelihood field.
One thing that strikes me here is when you look at those weights, and you've got a high weight on clear sky, and you got a relatively low weight on 700 millibar vertical velocity. First off, I question why would clear sky be considered to be a suppressant? That's one question I would have.
Yeah, let me. I have some comment there. We need to go back when NCAR wanted to develop this system. Actually, when they started to develop this system, they went to the forecaster at the field. They went to the forecaster at the field and then looking how the forecaster will forecast, for example, the initiation. This is where the likelihood comes from, because a forecaster, we humans, you cannot deterministically forecast, for example, the source at specific location at specific time. What you see, you look at all these data, you look at cape, you look at surface convergence, everything, and then you try to see where your data give you a likelihood of the initiation next hour or 2 hours.
Right, right. So like in the case of the origins, as I'm indicating of this, is that whether it's at SPC or NCAR or any given forecast office, experts have some nomograms or rule-based ways of forecasting convective initiation. So the first step that NCAR took was to develop an expert system which was just purely rule-based. If this, if this, if this, if this, if this, and automate that. The problem with that approach is that it's too sensitive to small changes in the rules. So then they went the next step and then incorporated this fuzzy logic framework, which sort of dampens down so that if one of these things is a little bit off, you don't the forecast doesn't flip completely. It's more stable in a sense. So the functions that John alluded to, all those I mean, each one of those things is the result of, literally years of deciding, how best to handle each one of those. And the weights themselves are also part of their, experts in trying to see what's the best weight.
Yeah.
But really the source of the skill is inherently goes back to the human forecaster. Really.
But if these weights have been fixed for how long?
These weight they did the experiment in several locations, and everywhere they went, they try to change the weight.
Change the weights based on. But when they use a small domain, when they go to Florida, they were typically operating in a Delaware-sized domain, not very big, and so with specific customers. So it was to their benefit to invest in tuning all these weights for a particular limited domain to get the highest skill, right? So that's basically how they operated, and to some degree may continue to operate.
Yeah.
But what we found was that when you start going out and out and out, larger and larger domains to a CONUS-sized thing, the sensitivity for looking at these verification sticks to these things is not that important. So what we found was these were good enough in the end of the day for the skill that we have found.
And these weights are there because they did try to tune the system on regime base, like cold front, warm front, dry line. With each one, they try to tune it for each own weight. And this one is the mix, combine everything. And what in our experience here, in the CONUS wide and everything, using the mixed tune weight work better than going, because the problem we have, when we are doing the tuning, we did some validation of the different mode, cold front, but if you want to have this regime in place, you need a forecaster to enter the boundaries. So that operationally we found is not feasible.
But the bottom line is you only got one set of weights for the entire domain.
That's right. That's right.
Yes.
Yeah.
That's pretty remarkable for a system like this, in my opinion.
Yeah.
But the system is based on the physical understanding how the convection develop, and the convection develop everywhere is almost the same.
We would like to, yeah. So this came out of the you could say the freedom that was won by saying we no longer really care in verifying the actual forecast. We're going to focus on this convective likelihood field, which has a, its inherent spatial structure is not 1 kilometer, right? It's broader, and subsequently, in looking into this, whether you compare the HER, for example, which is a high-resolution numerical weather prediction model, it does quite well, but its skill is also not. It doesn't verify well at 1 kilometer. You have to, look at the coarser scale, and I'm sure, LAMP, your convective products as well. You'd like to get down that.
Well, we smooth it.
Yeah, right. So, Bob, you had a question?
Well, it just seems like to me that now that you have done verification, you have essentially defined what you want to forecast. Maybe several things you want to forecast, but doing verification, you had to define that, and now you've done it. So now you've got a database where you could develop these weights by formal statistics and not by, let me say, guesswork. I'm not denigrating guesswork, because if you don't have any real firm objective as to what your verification is going to be, then that's good enough, and it's about as good as you can do, and so on. But now you've got a database, not only of predictors, but predictans, and you can go through formal statistics and do that. It may turn out that cloudiness is not important at all, or it might be very important. And I would venture a guess that when you have this many things going into that, that nobody can integrate that in their head as well as you can do by some formal statistical measure.
Right. Yeah, I completely agree. Yeah. We're almost out of time. John, do we have any questions on the?
Yes, I believe CS has a question. Go ahead, CS.
CS, are you there?
Yes.
Go ahead.
Do you mean you have only one set of weights for the entire U.S.?
Yes, that is correct, CS.
So this will be good for any time? So any different event season? Oh, I thought someone mentioned that you have a subset of weights for like North Carolina coast or Texas West Coast or Florida coast.
At one point, well, NCAR, who developed the system, would deploy the system in a limited domain over various parts of the country. And when they did that, they typically introduced new weights or attempt to finer tune in order to get the maximum sort of skill in these limited domains, whether they were in Florida or Colorado, for example. When John and Amma and Lingyan expanded this to the CONUS, we looked to try to find the sort of the best set of weights that would apply across the CONUS. There's some sacrificing and skill in doing that, undoubtedly, but in order to get it working for the whole country, and as you say, at all times and all seasons, you can't be, and it's impractical. And this was also feedback we got from the Aviation Weather Center. They need to look at a product CONUS wide, and they have to be able to interpret it CONUS wide. That what it means here generally means the same thing at some other part of the country.
So have these weights been fixed? How long have they been fixed like that?
It's a long time. NCAR has these for over 10 years.
Wait a minute. I thought you said MDL adjusted these weights.
No, we didn't.
No, the ones we're using here are the NCAR determined weight. We did do experiments with changing the weight, etc., prior to going CONUS wide. And we're able to get better skill in certain situations. But when we went CONUS wide, this turned out to be, the best fit, sort of the best skill for that scale, that domain size.
This is amazing because the weighting number looks so nice. 0.4, 0.1, 0.2. Looks like a perfect weighting number. Yeah. So what happened if one of the data file, one of the layer of the data, say it's inoperational anymore? So how going to arrange and change the weighting?
You mean if the data is missing? Is that your question?
Yeah. If it's either missing or inoperational.
Well, okay, to answer that, CS, there are only 4 sources of data for ANC. The number one, the largest percentage are the RAP data, which come in. If those data are unavailable for more than, I believe, 1 hour, ANC's outputs will cease. The second greatest combination is, or ingest of data is actually GOES East and GOES West satellite data. That's how we create the 2 cloud-based predictors. And again, I believe after 1 hour, if those data are not available, ANC cannot produce any output. The other two additions to the mix are surface METAR data. That's data of opportunity. If they're missing, it does not affect ANC. Also, National Weather Service radiosonde data, as they become available, are integrated, but again, data of opportunity. If they're not available, it does not affect ANC. So really, ANC will only be unable to produce output if there's a sufficiently long outage of either RAP or satellite data.
Okay, thanks, CS. We're past the top of the hour now, so we're going to have to wrap it up. I want to thank John Crockett and Aman Lingyan for a very interesting study and a very nice presentation. And I want to remind everyone that as soon as we get off here, John Chattel is going to take the recording of this and upload it to the VLab Forum website, so you can share that with your friends and colleagues afterwards, and he'll send out a notification when that's uploaded. And of course, you can share the slides, which are already up on the VLab Forum website right now. Coming up in July, we have a talk by Tony Mignoni and Rich Okulski about Wave Run-Up Project. And in August, we've got a talk about the just-in-time training plugin in AWIPS by Jason Burks. So please look forward to those, and we'll see you later on in the summer. Thanks, everyone.